great privilege to introduce Mike Filler. Mike is Associate Professor in the School of Chemical and Biomolecular Engineering here at Georgia Tech. He is the Traylor Faculty Fellow. His research, you'll hear a little bit about it tonight, but not everything by any means. He studies nanoscale materials important in electronics, photonics, and energy conversion, and many of them are based on silicon for reasons that I am sure he will explain. He's also the co-director of a group that I enjoy, the Community for Research on Active Surfaces and Interfaces, commonly known as CRAZY, and we get together periodically and try to come up with nutty ideas on things to do at surfaces of the materials. And a lot of what silicon is applied for has to do with their surface. Its surfaces along with its bulk properties. Mike is host of Nanovation, a wonderful podcast about nanoscience in the nanotechnology, in manufacturing and society. He is a recipient of the most prestigious National Foundation Award for Early Career Scientists, called the Career Award. He is a recipient of the Georgia Tech Sigma Chi Young Faculty Award, the Siegel Junior Faculty Teaching Excellence Award, and you will see why. And he is a Camille and Henry Dreyfus Foundation Environmental Chemistry Mentor. And before I bring him on, or ask him to address us, I want to read you a paragraph from one of my favorite books, called The Periodic Table. It is not one of my favorite books because of the title, or only because of the title, but because of the gorgeousness of the writing. It is by the Italian chemist Primo Levi, who is more famously a survivor of Auschwitz and wrote two of the most powerful books about that experience. But Levi was a practicing chemist throughout his life and wrote this amazing collection of essays, which I really encourage all of you to read. It's not technical in any nature, in any way, but it's about aspects of his life, and each chapter has the title of an element. There is no chapter, sadly, on silicon, but silicon is mentioned in a couple of places, and I want to read you a paragraph from my favorite chapter titled Iron, and this paragraph mentions silicon, but more importantly, it captures the essence of Mike. And it's about the character in this, the real-life character is Sandro Del Mastro, is the subject of this paragraph and of this chapter. Sandro climbed the rocks, talking about his predilection for outdoor rock climbing, more by instinct than technique, trusting to the strength of his hands and saluting, ironically, in the projecting rock to which he clung the silicon, calcium, and magnesium he had learned to recognize. He seemed to feel that he had wasted a day if he had not in some way gotten to the bottom of his reserve of energy. And then even his eyes became brighter, and he explained to me that with a sedentary life, a deposit of fat forms behind the eyes, which is not healthy. By working hard, the fat is consumed, and the eyes sink back into their sockets and become keener. I give you a keen Mike Filler.
Thank you. Good evening, everyone. Hopefully the microphone is on. Thank you to MG. That is clearly the best introduction I've ever had, so thank you. Thank you to Maureen Ruhi for helping to coordinate and the invitation, and also to Matt Baker for the invitation and for organizing this really great series. I'm here today to share a technological story you thought you knew. Okay, I'm going to tell it from my perspective, and I hope you find it interesting. So we're going to celebrate silicon today. We're going to celebrate how successful it's been as a technological material, but we're going to talk about its hidden history and what that history tells us about what might happen next. I'm an associate professor in the School of Chemical and Biomolecular Engineering, as MG said. And while I'm a chemical engineer, I too use the periodic table, and I figured we'd start this celebration of silicon by showing you where it is in the periodic table. To people in my community, we call this the group 4 column of the periodic table. Silicon turns out to be very related because it's in the same column as carbon and germanium. The name silicon comes from the Latin silix for flintstone, SiO2. That's the naturally occurring form of silicon. It's bonded to 2 oxygens because silicon loves oxygen. And you'll see that in a second. Berzelius was the first person to isolate more or less pure silicon. That took until 1823 because silicon loves oxygen so much. It's hard to break those bonds. The first commercial use of silicon began in the late 1800s to produce something called ferrosilicon, which I'll talk about in a minute. So we have a lot of silicon on this planet. in the upper crust of the Earth. This is the abundance of all the elements as a function of their atomic number. And you can see here circled in white is silicon. It is only second to oxygen because it's SiO2. And for every silicon atom, there are 2 oxygen atoms. If you don't believe me that we have a lot of silicon, just go to the beach. Right? Just go dig up some soil outside, which is not necessarily the purest form, but it is largely silicate-based. So that's the form that's all around us, 33% silicon, effectively an infinite quantity. We use it in construction and glass manufacture, among other things. Now, when we want to use silicon for silicon's sake, we have to work at it. Okay? Because those bonds are so strong between silicon and oxygen, we have to work hard to break it. We form what's known as metallurgical grade silicon. That is the first upgraded version of silicon. It is 98 to 99% pure. We would call this 1 to 2N, N meaning how many nines are in the percent. Okay, so 99% is 2N pure. You'll see that number later. We make a decent amount of this because it goes into steel and it's used in aluminum manufacturing, and those materials are all around us. How do we make it? Well, we take silica, the naturally occurring form, and we mix it with carbon. And we do this at very high temperature to drive this chemical reaction, where carbon will grab the oxygen from the silica and be emitted as CO2, leaving behind something that's a much purer form of silicon. We collect that and we'll do other things with it. That effectively is metallurgical grade silicon. This is done at very high temperature to break that SiO bond. That's what it looks like. It's a bunch of stuff that we then melt down and add into steel manufacturing, as I said, aluminum manufacturing, to do this. All right, so it's a minor component in steels, but it's a significant one in that it helps improve their processing as well as their durability. This wouldn't be a celebration of silicon without telling you what else silicon is used for. This is going to be a quick side point that if you do a little bit more work and you take metallurgical grade silicon and you process it a little bit harder with similar techniques, you can get up to 6N pure silicon, and we call that solar grade silicon. This is actually a relatively new route to this purity driven by the solar industry. So they need purities that are better than steel, but not as good as electronics, which will be the majority of my talk today. And in terms of the amount we produce, this number is rapidly increasing as we use silicon for this. All right, this is another story. It's equally as fascinating, in my opinion, about the use of silicon in solar technology. We are revolutionizing our energy infrastructure, and silicon is a key driver in that. I'll point out right here, and I'll come back to it, silicon is a horrendous light absorber. Right, so it's kind of ironic that we use silicon to produce the large majority of solar cells that are made. But that's not what we're here about today. What I'd like to talk about is the story of silicon electronics. And that story is often told as a story of materials, devices, circuits, and systems. And let me talk about each one of those for a second. I'll tell you what I mean by that. So we sometimes talk about the material silicon. And this is silicon's structure. It's the diamond cubic structure. It is identical to diamond that you might have in a ring, identical to germanium, except the atoms are silicon and not those other atoms. This arrangement of atoms dictates this electronic structure that's captured in what physicists call a band structure. These curved lines on here more or less tell you everything you need to know about the electronic properties of silicon when it's arranged like this. One thing I'll point out, I've highlighted in green here, is what we call the band gap. That's a region where electrons don't go. They're forbidden to be in that gap. And that's good because it means you can turn silicon off. And that's an important capability of a semiconductor. It conducts some of the time. We can control when it conducts. This band structure will tell you how good electrons move through silicon when you allow them to move. And that's going to be really important in electronics because we're going to create switches that control the flow of electrons. This is a plot of what we call mobility as a function of a couple different materials people have studied. Mobility is a measure of the speed of motion. Okay? So the higher you are in this chart, the faster electrons can move, and the faster switches can switch, and the better performing circuit you might get. Is silicon the best? No, it's not. Is silicon the worst? Certainly not. It's pretty good. And I'll talk more about that later. That's silicon, the material. Silicon, the device, is best embodied, in my opinion, by the transistor. Okay, so this is a transistor. This is a cross-section of a transistor. A transistor, for those who aren't familiar with it, is literally a switch. Okay? Current in a switch in your home goes from one terminal to the other, and it's modulated when you mechanically move that switch. We do the same thing in this device, and I've highlighted the different components of the device for those who aren't used to looking at images like this. So current is moving down here from the source through the channel and into the drain. That's like the entrance lead and the exit lead in the switch in your home. And the switch that we physically move in our house is substituted by this electrical switch we call the gate. Okay, so when we apply a voltage to the gate, we modulate how current flows down here. The silicon is all down here. This part is built on top of the silicon. But the silicon is central in terms of the behavior because that's where the charge is being transported. There are the three leads. Okay, that's the device, and we'll come back to the devices. When I take many devices and I interconnect them together to form a circuit, this is what it would look like in cross-section. So all the transistors are down here, and all these bright lines you're seeing are interconnects. These are wires that connect the transistors to each other to form a circuit that does logic or stores data or what have you. Okay? This is what's in your cell phone. This is an A11 Bionic chip produced by Samsung for Apple. If you were to look top down at a chip and look at those interconnections, it would look something like this. This is kind of a late model Intel chip. Really remarkable level of complexity. And modern chips today, the ones on your cell phone, have billions of transistors that are all interconnected. So it's really quite remarkable. That is at the chip level. So then we take chips and we build systems out of those chips. Right? This is a system we have with all of us, I'd expect many of us have in our pockets, a cell phone. We have processors, we have imagers, cameras, we have gyroscopes, we have all sorts of things in here made out of silicon. If you take many computers and you put them together, you might get a data center like this, which is what Google has. Right? 50,000 processors together create a data center. That's the system level story of silicon. And this has changed the world. This material, the devices built from it, the circuits built from those devices, and the systems built from those circuits. It's a remarkable story. But turns out it's getting harder and harder to fabricate the circuits. Let me show you a little bit about that. So there's something called Moore's law, which I put in quotes, but it's not a real law of physics. It's just something that we've ascribed to a trend, and that trend has been that over time we can put more and more transistors into chips. That's what that blue line shows you. And that's really great, and from that perspective, we're doing okay. From a couple other perspectives, we're not doing okay. These two curves that seem to have plateaued a decade or a decade and a half ago are describing the frequency at which we can switch transistors. The faster, the better. The faster you can switch, the faster you can do computation. But that's plateaued. And that's largely plateaued because we've stopped it from growing, because these transistors emit too much heat. And if we kept it growing, this chip would melt. So we stopped letting that grow, but we've been limited in how fast devices can run. For those of you who pay attention, you know the chips are always gigahertz and have been gigahertz for the last decade or two in their speed, whereas before it was slowly and steadily increasing. But probably the most damning thing is this plot. And I love that in this Economist article it was this little thing in the corner, but to me it's the most important one. It's the economics of making these circuits. We had a steady increase in the number of transistors you could buy over time for many, many, many years, until relatively recently. It's been very hard in recent years to give me more transistors for the same amount of money. Intel cannot make a new chip and say, hey, I put twice as many transistors on, but it'll cost you twice as much. That's not going to fly economically. So there's an issue there. There are other issues. This is a fab. This is where chips are manufactured. Ultra clean, because you have to prevent dust and things from falling on these chips when they're manufactured. A modern fab is $10 billion or more. Okay, fine. There's certain companies that can afford that, but there aren't that many. From an innovation perspective, it's really problematic, in my view and others' views, that we have 3 or 4 companies worldwide that can invest at this scale of capital. And when they do so, they are unlikely to want to be risky with their innovations. Okay, that's a real problem. The cost to design these chips in recent years has started to skyrocket. It's really becoming problematic to continue making more transistors per unit area. People have recognized this, and they've recognized this for many years. And so this is trying to show you a smattering of the types of different things people have tried to try and overcome what was this impending challenge of the end of Moore's law. Now, of course, people have predicted this for many, many years. It really seems like we're kind of getting there at this point. But people have tried different state variables instead of electric charge, maybe spin of electrons. Instead of silicon, there's all sorts of other things that have been studied. There's always a material du jour, okay, so whether it's graphene or some other material you've heard about. Maybe it's not that transistor. Maybe it's something that depends on the magnetic moment of a material that I can switch that on and off. That's another kind of switch. How do I represent the data? It goes on and on and on. We've tried everything. Right? And great science has come out of these studies. But it feels like this. Okay? It feels like we keep running into the wall. We have advances, and we try and bring them into manufacturing, and we can't. And I'm going to talk a bit today about what's going on here. In fact, it's so troubling to DARPA that very recently they've decided to invest another $1.5 billion into trying to overcome these challenges. And that's on top of the money the semiconductor industry already invests in R&D. So to me, this is quite striking that this initiative has been started. And it gets me thinking. The story we usually tell is about materials, devices, circuits, and systems. But what if that way of telling the story doesn't tell the whole story? What if it blinds us to future possibilities about ways to get around these roadblocks we're facing? And we're missing them because of the way we tell the story. What might be a better way to tell Silicon's story, or an additional way to tell the story? And what might that story tell us about how we can invent the future? Turns out clues are all around us. You all have clues in your pockets. Let's go back to the phone. There is a microprocessor, but then there's also a bunch of other chips in your phone that if you think about it carefully, you might say, why is that made out of silicon? Cameras, gyroscopes, memory. This is a cross-section of the camera in a relatively recent Samsung Galaxy S8 phone. Those big chunky things on top are pixels. Okay? The light comes in from the top and is absorbed by those pixels. This is a bit of circuitry underneath. There's nothing special about silicon. In fact, silicon's a really horrendous light absorber. So why are we using it for the camera? This is a gyroscope from the iPhone 4. A gyroscope tells you about orientation in which you're holding the phone, and it's doing that by measuring forces when you move the phone. There's nothing special about silicon in terms of the way it measures force. So why do we use silicon? And this one, I love these images. This is a modern cross-section of a flash chip made by Samsung. And what you're seeing here, I love this, it's entirely analogous to a skyscraper. They have built vertically 55 layers of memory bits. So each of these kind of bright lines you're seeing is another bit of memory. But there's nothing special about silicon in its ability to store data. There's materials that do it with less energy required, that do it on smaller scale so you can pack more bits per unit volume. So why do we use silicon? These things, to me, suggest that we're missing a critical chapter in the story we tell about silicon. And so this question I'd like to ask and continue this talk tonight is, what if Silicon's story was told as a story of process innovation, manufacturing innovation? And I think that story is critical and is often missing. What if there was this level in this previous chart that we haven't paid enough attention to in thinking about how we can invent the future of electronics? So let me talk about process as I dive into this part of the talk. What is process? Process is an interconnected set of steps that transform an initial state to a final state. That's a fancy professor way of saying it's how you make something, okay, is the process. What is process innovation? It's changing the steps that you're doing, and hopefully you're getting economic or some kind of performance benefit by changing the way you manufacture something. Now I need to stop and take a brief aside and tell you that process innovations are often hidden. And I would argue because they are hidden, they are often underappreciated. Think about the Stone Age, the Bronze Age, and the Iron Age. Right? We have these names for these periods of time because of the tools that were used during those periods of time. But I would argue that we probably should think about naming those ages after the process that was used to manufacture those tools. Because without grinding, without smelting, we would have never had the Iron Age or the Stone Age, Iron Age or the Bronze Age. The product embeds the process. That process is absolutely critical to enabling the product. There's another one that you don't think about ever, but it's why it's hidden. 100 years ago, the average store in the US might have looked something like this, where a customer would come in and interact with a single shop clerk, and that person would take your list of items and go pull them off of the shelf and hand them to you. That is remarkably inefficient compared to today's paradigm. What happened was we traded the direct interaction with the shopkeeper, and we made it harder on you. We said, go up and down aisles yourself and go find things. You don't think anything of it today, but you're being asked to do something that was more difficult to you personally than it was in the past. But what this enables by asking you to go get the items off the shelf is dramatic efficiency gains. Right? Very few people compared to how it was 100 years ago were required to service the same number of people. Right? And so you don't notice this. It's there. It's embedded in the shopping experience. Okay? That is a process innovation. I'm going to talk about 4 process innovations that are embedded in silicon integrated circuits. The planar process, monolithic integration, what's called the Siemens process, and Czochralski crystal growth. And I'll kind of give you a flavor for each of those. I've picked these 4 out because I think they are the most important in the current process of silicon manufacturing. There are a variety of supporting innovations that I'm not going to touch on. Okay, if you're interested in learning more, you can check out a website like computerhistory.org. It's a really phenomenal site. In the early days, people built things called mesa transistors. And they're called mesa transistors because if you've ever been to Arizona and you've seen the mesas, this is what they looked like, where you had this layer of semiconductors rising off of the surface in a mesa. These were not very good. Okay? These mesas had a lot of surface area that was exposed. That degraded the performance of this transistor. And the other thing that was really difficult to deal with from a manufacturing perspective was that you had to contact this 3-terminal device on the top, the side, and the back. And that was really a pain in the rear, okay, to figure out how to put electrodes in these different orientations. Who's seen this picture? I see all my students raising their hand. This is a picture of the so-called Traitorous 8, the founders of Fairchild Semiconductor. I think this is one of the most important pictures in the history of silicon. There are some famous people in this picture that you probably know. Gordon Moore and Robert Noyce went on to found Intel after changing the world, really, at Fairchild. I want to start, though, by talking about this gentleman here, Jean Erny, who you don't hear about too much. He invented a process called the planar process. Right? Before we had these mesas, they were built on top. He recognized that there was value of putting the transistor into the silicon. So this is his patent filing. And here was that piece of silicon. And he realized through certain processes you could put a source, let's say. And then through a second process, you could put a base region. And now you can see the basic structure of a transistor, right? 3 components here, 1, 2, 3. The other thing that happened in addition to putting these things into silicon was now you had a top surface that was flat. It became much easier to go and connect these 3 points with this top flat surface rather than having to make all these weird maneuvers with the wiring. So not only did he find a way to make the silicon perform better, the devices, because now they're protected from the environment. Those mesas were above the silicon, now we were in the silicon. But he created a planar top surface that made interconnection easier. You can go to computerhistory.org and you can see the lab notebooks that were written, the patent filings of all of these folks. Really a fascinating read. They recognize the value of doing this at the time, and it's all written out there in their own handwriting. This innovation led Fairchild to have significant performance advantages relative to competitors in the days of single transistors, back when they would sell single transistors. These are great ads. But I like this ad not for the fact that it's from 1958 in a magazine called Electronics. Like, you'd never see this in time. Well, you don't have magazines anymore. Who am I kidding? So, but it's the fact that this was selling single transistors. Bob Noyce, who worked at Fairchild, as I mentioned, helped found it. He realized the value of Ernie's innovation in connecting many devices. So not just one, but putting several devices. So here's one device, and here's another one. Now they're embedding multiple things in the silicon. Okay? And not only did he realize that you could do that, I think that was fairly obvious. He had to find methods to prevent them from talking to each other through the silicon. Right? He had to find ways to isolate them. And that was a key innovation that Bob Noyce brought forward. In addition to leveraging a technique known as photolithography to start to put down the metal wiring to create the circuitry. So what you're seeing here is this top view of a silicon wafer. The transistors are embedded inside it, and this is all the circuitry that is connecting the transistors that he put on top. So Ernie's planar process made the devices good, made the top surface flat, allowed you to put many in a surface, and now interconnect them. And this was the first monolithic integrated circuit. We still today make circuits this way. You can read his lab notebooks as well. So the next part of this that is really important to recognize is that integrated circuit manufacturing is an entirely integrated process. Of course it is. It's called an integrated circuit. But this is important. Because of the way Ernie and Noyce decided to start building things, where they put things into the silicon, there now became no way to remove any defective transistors. There's no way to carve them back out when they don't work. So you can't remove them. So what does that mean? That means that the processing of every single one better be perfect. You can't make mistakes along the way. And not only does the processing have to be perfect, but that silicon layer where the charge is being transported also better be perfect. Let me take away those labels. Right? The charge is moving through here. If you had a defect in the silicon, an impurity atom sitting there, the electron would see that impurity and scatter off of it, and your device would be degraded. If you had a defect in the crystal where the silicon atoms weren't aligned properly, that would also be another scattering center where electrons would be prevented from reaching the other side of the device. All of these things lead to degraded performance. So what do? We had to make the silicon more perfect. And we started by reaching electronic-grade silicon. Right? Before we had 6N, that sounded pretty good. Now we're going all the way to 9N to remove all those excess impurities that would cause scattering of the electrons as they move through the channel. I will also point out, since we're celebrating silicon, that this is where we get silicones from. Okay? This part of the process is where we take part of silicon and use it for silicones. I'm not going to talk more about that, but just to recognize that that is a non-negligible part or use of silicon today. This is the so-called Siemens process. And you all are glazing over, so I'm going to simplify it into a couple of pictures. What we do in the Siemens process is fairly straightforward. It's a lot like distilling water, except we do it with silicon, and it's a very extreme version of distilling water. So here is that metallurgical grade silicon, 2N pure. If we react it with hydrochloric acid at a moderate temperature, we can turn it into chlorosilanes. We turn it into a gas, just like we do when we distill water. We put water molecules into the gas phase. It leaves behind the impurities. Okay? So these red dots are meant to be impurities. They don't go into the gas phase as readily as the silicon atoms do. There is another purification step that happens here, but Bottom line is we then take that gas where we left the impurities behind and we redeposit it down to form the solid. That is 9N pure electronic grade silicon. It's kind of a crazy number when you think about it. Parts per billion or better. That's ultra pure silicon. But that says there's no impurity atoms. But what about those defects? So now we need to align all the silicon atoms that have been purified in exactly their right locations and none out of place. And this is where the fourth process innovation, Czochralski crystal growth, comes in. This technique was invented in 1916 to 1918 at a metals company. They had no interest in silicon. It was far too slow, far too expensive to be used for metals at the time. No one needed this kind of purity. But in the 40s and 50s, people started to recognize the value of this growth process to create really perfect ordered materials. Basically what you do, and it's been adapted for silicon since Czochralski's time, is you take that really pure electronic grade silicon, you melt it down at high temperature. You add a seed particle that is where silicon starts to deposit. And you do this at a temperature really close to equilibrium. Very high temperature, and so it's a very slow deposition process. And if you do that really slowly, the silicon atoms will go only where they're most favored to go. And that, if you keep pulling the crystal, you can create these boules of silicon, that are really remarkable. This is the purest material man can make, both in terms of its compositional purity and its crystallographic perfection. That's all so the electrons flow uniformly because we can't get rid of bad transistors. That's what a process looks like today. It's been highly engineered since it was first used. And in fact, we get a bump in purity up to 11N. And that's because the impurities tend not to want to go into the silicon lattice when crystallization happens. We take out these boules and we slice them into the wafers, and these are the wafers on which we build the transistors and then the interconnections. So these were the four process innovations. The planar process to make things flat and protect the devices, monolithic integration to make a circuit, the Siemens process to purify silicon, and the Czochralski growth process to make the silicon atoms all where they're supposed to go. These four processes have underpinned integrated circuit manufacturing for 60 years. All semiconductor R&D spending, over $65 billion from industry in 2018 assumes these four processes. And these four processes incentivize certain kinds of circuitry. But we know we have these problems. We know there is a strain in the system. We know we keep running up against the wall when we try new materials, new device physics, etc. And we know there are certain things that silicon can't touch. Wouldn't it be great if when we pulled a tissue out and blew our nose, we could have a sensor that would detect whether we were sick and would wirelessly communicate that data to our doctor? Silicon can't do that, at least today. Wouldn't it be great if in every pill we had silicon, a very small amount of silicon that hopefully didn't harm our bodies, that when you took the pill would wirelessly tell your doctor you took the medication you were supposed to take today? Wouldn't it be great if we had sensors on many, many seeds, if not all the seeds in this field, to detect when they germinate to improve the efficiency of farming? Wouldn't it be interesting to think about buildings and structures as their own data centers, to kind of fill them with electronics rather than these data centers that are very localized today? There's a lot of things silicon can't do. For all the things that it's amazing at, today's processing can't do many things that would be really great. So here are two axes this is kind of engineering 101. This is the manufacturing scale. So if you want to do Kleenex, you've got to be way up here at large scale. And this is performance. If you want to do wireless communication, you have to be a high-performing device. Silicon is a good performing material, makes good devices, good circuits. We know that. We don't produce it on very large scales compared to the scale of buildings, the scale of farming. We've tried all sorts of other materials over the years, and we seem to be stuck on this line. We can't seem to find a combination of materials and performance that gets us to this space where these new technologies might become possible. So why is silicon still king? It's not good at some things. the system is straining under load, it's king because its processing is perfect. The processing has to be perfect because of the way it's processed. Other materials fundamentally can't compete with the perfection that has been developed over 60 years. And I would argue that any attempt at perfection is likely to require a similar investment over a similar time frame. So what's needed? How do we get around this problem? I don't want to wait 60 years for the replacement to silicon. Let's look at how other industries manufacture things. Let's take the food industry, for example. Right? Ever wonder how the grocery store shelves look that good? Partially because there's employees who stack the vegetables like this. I don't stack my refrigerator like this. But it's also not because nature is perfect in making food. Right? Nature is really not great at making all the tomatoes the same size. Right? So we have methods to separate the tomatoes that are of incorrect size, basically. Right? And your definition of incorrect will vary. Right? Remove tomatoes that have some bite chewed out of it by an animal or what have you. Right? You never see that in the store, but we have methods to remove it. Take rivets, particularly for high-value applications like automotive or aerospace. We have ways to sort bad rivets from good rivets. My industry, the chemicals industry, this is how we operate. We make things and then we separate stuff. This is probably the most important process you never knew existed. This is oil refining, basically, also known as fluid catalytic cracking, where we take crude oil and we break it apart into a whole bunch of pieces. And they're all mixed together. We don't care. And then we separate them. We take gases like propane off. We take gasoline, which is a little bit longer chain hydrocarbon. Even longer still becomes oils, etc. We don't waste anything. But we have methods to purify what we've made. Right? All other industries assume imperfection. All other industries have methods to separate imperfect components. And those components, I'll point out, are modular. The tomato is a modular piece of food. The rivet is a modular item. And a molecule is also modular. I'll also tell you that separations consume 15% of worldwide energy. So if you were ever wondering whether this was a big deal or not, it's a huge deal. Right? We separate everything in pretty much every industry except silicon. This is what we've done with silicon. It's a tremendous success over decades of work by many engineers and scientists, and we have dropped the cost of silicon by orders of magnitude. Right? That's the story of the materials, devices, circuits, and systems. But if you compare this to other things that we process in different ways, and now I'm plotting it not per transistor, but per a mole of transistors, 10 to the 23 of them, it doesn't look as good. In fact, when I compare it to molecules, even advanced things like a pharmaceutical Lipitor, the cholesterol-lowering drug, which is a multi-step synthesis and separation, 10 orders of magnitude cheaper to produce that pharmaceutical. These are modularly manufactured with separations and removal of bad components. Here it's fully integrated manufacturing. We have to be perfect because we're embedding things in the silicon. So our question, and the thing my lab has been working on in collaboration with others for the last several years, is asking the question, can we introduce modularity into processing of high-performance electronic devices and circuits? And if we can, what technologies might be possible with this more modular circuit processing paradigm? And there's going to be some science and engineering needed to do this. So we first have to modularize the transistor. We have to take it out of the silicon so it can be a component that we can throw this way or that way. We have to be able to move it around effectively. Okay? If it's in a wafer, we can't move it around. We're going to need to be able to separate transistors. And ultimately, to make circuitry, we're going to have to connect those modular transistors. So let's talk about those three processes for a minute or two, and I'll show you some data from the lab. How do we modularize transistors? Another way of saying that, or something that's related to this, is processes to make transistors make themselves. Okay, we want to grow transistors just like we coax molecules to make themselves in chemical reactors. This is the device again. I'll focus here for a second. We've got to make source channel drain. My group spends a lot of time growing crystals, and we use a technique that's called the vapor-liquid-solid mechanism. There's a vapor out here. There's a liquid seed particle that collects material and injects it into the solid semiconductor. And the great thing about this technique is that we can change what's in the gas phase. So we can make silicon, and then we can add in a dopant, and we can make a region that's doped. And then we can take that dopant out and make a region that's undoped. And you can see some work here from my lab exploring this ability to modulate the composition or the structure along the length of nanowires using this capability. But you can look at this and you can kind of see, if you turn your head to the side, source, channel, and drain. All right, so we're doing that. Gazda, great postdoc in the lab, has been working on advancing this technique in our group. That's a wire she grew, and it's encoded with a structure that looks like source, channel, drain. But you shouldn't believe me because it's just an SEM image of the exterior. But if you put this in a selective etchant that is selective for certain regions and not others, you can remove some of the silicon in the channel region and leave the silicon in the other regions to show that it's compositionally modulated, just like a transistor would be. Okay. She can do this till the cows come home. So we can grow crystals from what we call the bottom up with source, channel, drain, until you're blue in the face. That's that part. And that's a key part of a transistor. But there's this part. Right? And normally in the field of nanoscience, what people often do at this point is resort to kind of the older, not older, but the techniques that we use traditionally in the industry to pattern that gate. But to make that modular component and to make it cost effective, you want to eliminate that process, which is known as photolithography. So how do we do that? How do we take what Gazda has done so beautifully and go the next step to create the gate stack? And we're not entirely there yet, but this is what we're doing. Here's that same kind of modulated structure. There it is to prove to you that it's a modulated structure. But we don't want the modulation. That's just really to reveal that we have the source channel drain structure. Amar has been doing this work, and we're really excited about this. He's coated a special resist material around the wire. And then he's used an etchant that comes in and doesn't etch the wire, but it removes this resist only from certain regions. Right? This is actually, to our knowledge, the first time this kind of thing has been possible with the kind of precision Amar has. The programmability. The cool thing is there's still source channel drain in these structures. And now that we have this mask that's protecting the source and the drain, we're working on depositing the gate. But we have a pattern with which to do so, and we haven't had to use photolithography. We now need processes to separate transistors. Right? It's not enough just to make them. If I have a batch of them, I know I'm going to assume they will be imperfect. They won't all be the same in their properties. And so what I really like to do is not throw some stuff out, but fractionate, just like we do in oil manufacturing, where we have some transistors that turn on at this voltage, some that turn on at that voltage, and some that turn on at this voltage. This is a really challenging problem to figure out how to purify electronic components based on the electronic component's property. But we're making strides with our collaborators at Rutgers, where they've developed this really beautiful technique for using electric fields to rotate materials, and through their rotation they can back out what the conductivity is of different wires, which is really phenomenal. And it shows us, in fact, that in the wires we grow, there's a distribution of properties, which is something that we could hopefully narrow. That's always a goal, is to narrow that distribution. But we can also, now that if we know there's a distribution, we can separate them. Okay? And so we're working on techniques to do this. And finally, we're working on ways to take these modular components when we have them and interconnect them to make circuitry. By the way, to do that, you would think about something like a transistor ink, where instead of printing black material to form the letters on a page, there's actually transistors in that ink, and you spit them out in a printer and then interconnect them. We work with a great mechanical engineer, Kira Barton, at the University of Michigan. She is an expert in this technique called electrohydrodynamic printing, or EJet printing. It is kind of like inkjet. Inkjet uses a pressure differential to force ink out of a nozzle. They use an electric field to pull inks, or whatever material they're working on depositing. And by pulling, you can get much finer features. And this is just an example of some of the features that are possible with this EJet technique. And it's really critical to have fine features, because as we build better and better transistors with the process that Gazda and Amar are working on, we're going to need to contact finer and finer things. Okay? So this is a technique that should allow us to achieve that interconnection. This is overall the modular process we're pursuing. Make these modular devices, make many of them, and I'll talk about that before wrapping up. Transistor purification, and then print and interconnect. Okay. None of these are easy. I don't have the answers for all of this yet. It's going to take a few years. But this is where we're going, and we think by rethinking the process that there's exciting new things you can do. So what things? Some of you may be sitting there saying, I don't see how you're going to get 5 billion transistors interconnected with your approach. And you would be right. All right? So this is another one of these axes. This is, again, is manufacturing scale here. And this is level of integration. Right? How many transistors can we interconnect? And the way we do it today is down here, relatively small scale, highly integrated. What we're trying to do is not going to be there at all. It's going to be up there. It's going to be large manufacturing scale and much less integration. But that's okay. There's really exciting things you can do when you rethink what you should make with devices that you have that are really low cost and effectively disposable. This is work done by our colleagues Gregory Aboud and Thad Starner. Really, they didn't do the work. Who am I kidding? Nivedita, who may be in the audience, did this really, I think, groundbreaking work to show that you could make a very simple autonomous wireless sensor with a single transistor. We're all used to Bluetooth. We're all used to the communications with our cell phones. That requires hundreds and thousands of transistors. They developed a very ingenious way to use a single transistor. The transistor they use, though, is one of these expensive single package transistors. And wouldn't it be great if you could just print out that transistor while you're making this little sensor? They can detect, by the way, audio a kilometer away with a single transistor using this technique called backscatter. So I think if we think differently about the systems and the circuits we could design, there's lots to do. Now, will it always be one? Probably not. We think we can get better. Right? We can think about things that have tens of transistors like ring oscillators or amplifiers. In the long run, hundreds, thousands, who knows? Right? There's a lot of things that Bob Noyce and Gordon Moore and Jean Erny did not predict would happen when they started developing their process. The last thing I'll kind of leave you, well, I'm going to skip this because of time. No, I'm not. I'm going to go back. Sorry, because this is an important piece of the story. So even though individually it may be a relatively simple circuit, if you put many, 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 many circuits together, the system can be significant. And I think that's something that's generally missed when we talk about simple circuitry. If you think about the system, which may be a data center, or it may be a whole bunch of interconnected nodes that permeate your house, right? It's going to be the number of transistors on each node, and then the total number of nodes that you can deploy. Right? Today, what we do in integrated manufacturing is we have lots of transistors per circuit, and relative to producing chemicals, a low number of circuits that we deploy. What we're arguing for a more modular manufacturing approach is that, yes, we know we'll have fewer transistors per node, but we think we can potentially produce these at very large scale, and they can talk to each other if they can wirelessly communicate. And you can think about billions of sensor nodes that then communicate to form a system. And now this is looking way out, but we don't think we should be limiting ourselves to simple circuitry or at least simple systems in the long run. But if you're going to put these things in buildings, how do you produce enough? And this is great work done by Maritza Mujica in the group. She's been developing a process we call the geode process, and that's a geode. Right? And what we want to do is grow transistors just like these crystals grow in this rock. Okay? Our geodes are not that big. They're not macroscopic. They're more the size of the human hair. This is a dispersion of the geodes that Maritza produces in the lab. And what goes on in each one of these spheres is wire growth and ultimately transistor formation. The bottom line is we take the little seed particle that drives growth, we put it on the interior of the capsule. Kind of looks like this. We allow the gases that do the growth of the transistor to go through that wall. But we take that powder I just showed you and we load it into a more traditional chemical reactor. We process it as we would process a chemical. I don't view transistors any different than chemicals. We pull them out. They're now geodes because there are crystals, but not any old crystal. They're silicon crystals and ideally silicon devices like PN junctions and perhaps more advanced things. To give you a sense of the scale we think we can achieve, simple back-of-the-envelope calculation that in an average 1 meter cube reactor, we can produce as many devices in one day as the entire semiconductor industry produces in 1 year. All right, so in terms of can we hit high manufacturing scale with these processes, we think we can. So the last thing I'll leave you with is this story. You might have seen this movie, The Social Network. That's Justin Timberlake playing Sean Parker, the founder of Napster, who was an early investor in Facebook. And he's talking in this scene to the founders of Facebook. And they're all excited because they're going to make $1 million. And he says to them, $1 million isn't cool. You know what's cool? $1 billion. And they're just like, whoa, right? Right. Current state-of-the-art integrated circuit, 4.3 billion transistors in your pocket. But 1 billion devices isn't cool. You know what's cool? A septillion devices. Thank you for your attention. I'd be happy to answer any questions.
Challenges that you are facing when you're making presentations for your proposals to the people that have the money to fund this kind of research.
Right. This story is a hard story to tell. This is this hidden story, right? The usual intros to manuscripts that people write are much shorter, right? It's hard to tell this story. Process innovation is hidden. So particularly in this case, it can be really challenging. It can be challenging when people view the world through the integration that's possible with silicon, which is truly remarkable. I'm not, nothing I've said here should take away from the success of the semiconductor industry. But yeah, so we try and find ways to convince people who fund things in certain areas that this can be applied to that. And we come up with ways to market the material in a way that would resonate with them. I would never present this way to many program managers I talk to, right? Because it takes too long, and their biases are often not in this direction, right? One of the reasons I accepted this, beyond just that it was a great opportunity to share what we're doing with a bunch of people from the community, was also to put together this broader story, to be able to tell people how we think about the world. So I don't have any really great answers, just to say that it's challenging to start, challenging to convince people. Everyone wants you to show them that you've done it already, and none of this is easy. So it's not perfect, but we keep trying. We try different angles, and as of late, we're starting to see a bit more progress, which is good. And I think in the fact that Moore's Law is kind of ending and people are trying all these different things, there's a ripe opportunity to try this.
I see you. Is it on? Okay. I see you collaborated with a lot of other groups of people.
Yeah.
How do you manage to, number one, find out what other people are doing and get them to share? That's a challenge right there.
Yeah, we have a lot of lunches. So for every one person I collaborate with, I had lunch with 10 people, right? It's one of those things. It's just like any personal relationship. It's finding people who are doing synergistic science that you get along with and that you have similar values in terms of what's important in science and how you conduct science. We're lucky at Georgia Tech. Georgia Tech is a really phenomenal institution because we have people literally doing everything because we're so large. So whereas someone at a small school would have to immediately go off campus to find expertise, there's a lot of expertise right here. When we don't have that expertise, we go off campus. The story of Kira Barton is a really interesting one. I had her on the podcast that MG was talking about. Had no idea that she would have a skill set that was so synergistic with what we were trying to do. And in the after show, we started talking and I realized really quickly that this person needed to be part of the team. And so then invited her and convinced her we were good to collaborate with and we were doing cool things and she's part of the team. So it's really kind of a stochastic diffusion kind of process like most things. But we're lucky at Georgia Tech because we have a large number of really great people doing lots of different things.
You mentioned that there's an abundance of sand. With all the dredging of beaches and the reduction of shorelines and concrete and buildings all over the world, is there potential a shortage, or is there a special kind of sand?
Yeah, it's a great question. So there's definitely no shortage. We have sand out the wazoo. So we could build for the next 1,000 years and we'll be fine sand-wise. The sand that's used in silicon manufacturing comes from a couple specific locations. It may even be just one. And I'm not an expert on this, but I've heard before that it comes from a very pure form of sand that you can get in like Minnesota or something like that. Right? Yeah, it's a great question, and I can't remember the exact place, but they do look for things that are more pure, right? They're not going to go down to Home Depot and get the sand for the sandbox. It's a different kind of sand that's used. Yeah.
Hey, Professor, you had a great talk. I have a question that, so we are focusing on different kinds of resources. For example, we know uranium, but people also made nuclear bomb from that. So what do you think, like, these kind of resources in future years, people are building so much stuff, but what do you think about the applicability of these things?
So the question I think I heard you ask is, what's the downside of all this? Okay, so I think with every technology, there is an upside and a downside. And you have to manage the downside risk. Because if you just choose not to do any technology, then we're kind of back in caves. Right. So, but yeah, so there's a lot of good that can come from manufacturing efficiency, having sensors to, on the crops and all this kind of stuff, right? But there's the downside, right? When I said, would it be great if that building was the data center, half of you were saying, oh man, I would not want to put my data in my friend's house, right? I know how he keeps his house. So there are going to be concerns about this. I think there are already plenty of concerns. You could even argue that this approach may be used to mitigate some of the security risks we have today. If you have disposable stickers that have circuits in them, there may be ways to do certification and authentication in entirely new ways that are not software-based. Right? There's these kinds of things that could emerge from a technology like this. It's hard to predict where it goes, but I'm one of these folks that says you just have to manage the downside risk.
All right, one more question.
One more.
We'll take one more question.
So my question is also kind of similar to the first one that was asked. So you're kind of, when you say that we can manufacture chips through and transistors through a modular process, then that's like a massive paradigm shift, because the reason you can make tomatoes that way is that no one cares about the precision of a tomato. So this is like really asking for a way to rethink circuits, and I think it's an incredible place to start. But do you think, how do you think we should start on something like that? It's a very big question to ask.
So I think the way we started isn't so bad in terms of picking a place to start. Yeah, so I think nanotechnology, right? That's my group studies these crystal growth processes and these surface processes to pattern those crystals. That's my group's main expertise, right? And I'm a chemical engineer, so I love process in my heart also. So I feel like the kid in was it The Sixth Sense? I see dead people. Right? I see process, right? That's, but I think students in my class right now up here laughing. So I think nanotechnology and nanoscience has gotten to a point where it's time to take it out of the lab and try and use it, particularly the very functional things like transistors. We've demonstrated these things. So the wires I showed you, we've made those for a decade or so. The community has. And we've done largely the old techniques in terms of building stuff. But we know they're really good when you make them the old-fashioned way, right? Or at least take a wire and then use the old-fashioned processing. So we've struggled to make it the next step. And so part of this is recognizing, though, that we know enough about surface chemistry, we know enough about nanomaterials growth, we know enough from the chemicals industry to think about separations, that we can start to put it together. In fact, if you look at some of the roadmaps for nanotechnology, a lot of them say we need a compelling application. Yeah, we've done all sorts of amazing science, and we understand materials way more than we did 10, 20, 30 years ago when the nano push started. But finding that compelling application space so that we can drive directly to the innovation and get industry on board has been difficult to materialize, particularly for the functional things. We put graphene in lots of tennis rackets and mattresses and things like that. But in terms of this kind of space, we struggled to do that. And so we're trying to do that. It's going to be one of these diffusion processes. But once we can demonstrate a few more of the key pieces, and we've already made nice progress, hopefully people start to pay attention. So we'll see.
All right, let's thank Professor Filler again for that inspiring and very interesting talk. And we have a little gift for you, Mike, from the College of
Thank you.
Sciences.
Thank you very much.
So thanks again for agreeing to give this talk. Now I promised gifts for some of the rest of you as well. So if you look in your program that you should have gotten, everybody has a star on page 2 of their program. They're different colors. And if your color is blue, you have a blue star, you are a winner. And you can go into the bag. You can see Maureen over there.
If you have your blue star, raise up your program so I get a picture.
Yeah, we'll get pictures of all the lucky winners, and you can see Maureen to get your T-shirt in the back. And by the way, let's thank the College of Science staff, especially Maureen, for organizing, booking this room, publicizing the event, doing the social media. Remy and several others in the College of Science staff. Thank you so much. So that concludes the program. There are refreshments in the back, and thank you all for coming.